Welcome to the lecture of Control System 2, and this is our third lecture. So last class or last lecture we have discussed about introduction to state space representation, and I told that we are going to discuss the introduction to state space representation. Then we will introduce the concept of state variable and state model, and we will discuss the concept of state variables and state model using some motivating examples, and ultimately we will define what are the definitions of state vector and state space. So we will continue what we are discussing, that basically in the last class we have discussed to give the answer of this third question, that what wrong can happen if we always assume initial conditions of a dynamical system 0. So basically we have tried to answer of this particular question. So now we will start from here, and if we will go back to the example what we are discussing, that we have a cascaded system having transfer function HCS equal to S1 minus 1 by S plus 1, and another subsystem we have, that is HFS is equal to 1 by S minus 1, and we have tried to represent this system or these subsystems rather using two first order differential equation, that is x1 dot t is equal to minus x1 minus 2 vt, and x2 dot equal to x1 t plus x2 t plus vt, where vt is the input of the system and the output of the system yt equal to xt. And here a couple of things we have to observe, that we have assumed along with this input and output variable of the system, we have assumed some other variables which we have named as states of the system, but till now we have not formally defined what do you mean by the states of the systems. But we have observed couple of things during the discussion or during the analysis of this particular system. So along with the input output, we have defined these two variables named x1 and x2, and we are calling it states of the system. And once we have defined and we have tried to write the system dynamics as a first derivative of these two system states, that is x1 dot and x2 dot. And another very important thing, if you observe the output expression, if you go back to the output expression of the system, that is y of t, you will find that if any time if we want to determine the output of the system for t greater than 0, suppose at any time if we want to determine the system output, we want to know what is output y of t for t greater than equal to t0. If we want to know this one, then what are the things we require to know? We have to know the input quantity, we have to know this input, what is the input. So we have to know, first thing is we have to know v of t, what is the input to the system for t greater than equal to t0. And we have observed that this input is not sufficient to describe the system output for t greater than equal to t0. Along with that, two important quantities we have to know, that is x10, we have to know the x10 and x20. What are these x10 and x20? So these are the initial conditions of the system state variables. That is, if you go back to the differential equation, you see, so we have described the system output. When we have described the system output, then we have observed that not only this input is required to be known, along with that we have to know the initial condition x1 of 0 0, which we have assumed that some value, some non-zero value x1 of 0, and along with that we have to know x2 of 0, some non-zero value, that is x2 of 0. So these are the two things we have to know. So now again I am summarizing the things. So here to describe the system, we have taken the help of two variables, that is x1 and x1t and x2t. Once we have defined the x1t and x2t, we have tried to write or we have tried to describe the system dynamics as a first order differential equation of that or those state variables. And also we have observed that to describe the system behavior along with the input, we have to know the initial condition of those state variables, that is x1 of 0 and x2 of 0. So along with this idea, we will further explore that to define formally what do you mean by the state of the system. So let us continue with today's lecture, that the concept of state variable and state model. So as an introduction, we can again recap that a mathematical abstraction to represent or model the dynamics of a system utilizing three types of variable called inputs, output, state variables. Means whenever we are going to represent any system in state space, we require three informations. Input, you have to know what are the inputs to the system, you have to know what are the outputs of the system, also you have to define the state variables of the system. So till now it is not very much clear to us that how to identify the state variables of a system once the dynamical system is given to us. So that we will probably today we will discuss along with two examples. Now again we will to begin with that how to identify or how to understand what are the state variables of a given system. Let us try to understand what are the advantages of state space technique. So this approach can be applied to linear or non-linear, time variant or time invariant seesaw or MIMO system. So these things already at the first lecture we have pointed out that state space technique is more generalized technique, where we will see later on that linear, non-linear, time variant, time invariant, seesaw as well as the MIMO systems can be represented. And most importantly, that nth order differential equation can be expressed as n number of equation of first order whose solutions are easier. So here any nth order dynamical system can be represented by nth order differential equation. So now with the help of these state variables, later on we will see that this nth order differential equation, with the help of state variables, we can convert it in number of first order equation, and it will be easy to solve the n number of first order equations using computers also. So later on we will see also these things, that how a nth order differential expression means nth order differential equation with the help of state variables, how we can convert it in number of first order equations. And it is a time domain approach. Several times I have pointed out this method is suitable for digital computer computation because this is a time domain approach, and also all the modern controllers with optimization technique can be designed once the system is represented in state space. So now some few of the things we have to verify what we have claimed. Definitely as the course will progress, we will see all the claim or whatever the advantages we have stated about the state space technique. So now we will start with the first example to understand that what do you mean by the state variable for a given system. So to understand that one, we have taken a mechanical system. Suppose we have a mass m. So this is the mass m, So this is the mass m. Now we are applying a force u, so that force actually represented by u, or you can say that a force is applied, that is capital ft. Now once you will apply a force in this direction to a mass m, and if you assume that there is no friction, actually here some die friction can act, so we are assuming there is no friction. So now or we can assume that some of the disturbances may act. So now onwards, or for the time being, we will assume that that disturbance f of xt is equal to 0. We will not consider any disturbance to the system. So consider a simple system, that is a mass m, and we are applying a force, that is the input to the system, that is ft. So what will be the consequence if we will apply a force to the mass? Then there will be a displacement, okay, and that can be represented by xt, or the velocity, that is v of t. Fine. So consider the mechanical system shown in the figure, where the mass m is acted upon by a force, by the force ft, that is the input to the system, that is ut. Then applying Newton's law, easily we can write the dynamical equation which is describing the dynamics of the system, that is ft equal to m into d2xt by dt2, where xt is the displacement. And the same equation can be written in the form of m into dv dt by dt, because we know that the velocity vt is the derivative of the displacement dxt by dt. Okay, v of t is equal to. So now as already stated, xt and vt is the position and the velocity of the car respectively. The above equation can be written as, so this is a second order differential equation. Now this second order differential equation can be converted into two number of first order equation. How? Now we know that dv by dt can be written is equal to 1 by m into ft. You see, we have written ft equal to m into dv by dt, so we can write dv by dt is equal to 1 by m into ft. So this is the first order differential equation, single equation. Another equation we can write that how the xt and vt is related. Now we know that dxt by dt is equal to vt. So these two equations are also describing the dynamics of the system, as this second order differential equation was describing. Okay, now let us let us go forward, and what is our objective here? That has to be clear. Now objective here to compute the displacement xt, which is our output variable of the mechanical system at any time t greater than t0, if we know the applied force ft, that is the input variable from t equal to t0 onwards. So now actually we want to know what is the displacement of the system if we have applied a force. That force is known to us, that is the input to the system t equal to t0 onwards. Now another thing coming into our mind, to do this, any additional informations are required to complete the displacement xt of the mechanical systems or not. Means we know the input, but along with that something else is required to compute the displacement xt for t greater than equal to t0 or not. To do that one, we will do the further analysis. What is that? Now we got the first relation 15a, that is dvt by dt is equal to 1 by m into ft. Now if I want to determine what will be the vt, then vt will be the integration of the right hand side. So now you see Vt is equal to 1 by m integration minus infinity to ft dt. So that is very important to note down, that we have started doing the integration from minus infinity to t. So now if you see the timeline, that we want to know the system behavior from t0 to suppose t0 onwards. Okay, so t0 to plus infinity, we want to know how the system will behave. Now we know the ft from t0 onwards. Okay, means ft is the input of the system, but we have started doing the integration from minus infinity to t, means at any time t, if I want to know, for any time t, if I want to know that what is the system behavior. So why we have started from minus infinity? Because we want to know if it is a dynamical system. So the behavior of the dynamical system depends on the past inputs. So if the system was driven by the past inputs, then that also has to be taken care when we want to know at any time what is the displacement as well as the velocity of the system. So that's why we have started the integration from minus infinity to t, which again can be decomposed in two parts, that is minus infinity to t0 and t0 to t. So now what is 1 by m minus infinity to t0 ft dt? So this part is representing the initial velocity v of t0. So this part is representing the initial velocity. So that's why we have ultimately written vt equal to v of t0 plus 1 by m t0 to t ft dt. So after knowing the expression of vt, now we will try to calculate the displacement, because that was actually that was our objective, that we want to know what is the displacement of the system. So now we will consider the 15b, that if we want to know the xt, then we will integrate vt from minus infinity to t. You see, we have integrated minus infinity to t. So now same way we will decompose this integration in two parts, that is minus infinity to t0 vt dt plus t0 to t vt dt. So now this representing the initial velocity. So we have written that initial velocity x of t0, and from t0 to t we have to integrate vt dt. So now already we found out what is expression of vt, and we will substitute this expression in the place of vt. So now in the next line we have done that one, and ultimately we have found out the expression of xt. So this is the last 17, the equation number 17 is the expression of the displacement. Now you closely observe that if any time t greater than t0, if you want to equal to t0, if you want to know what is the displacement of the system, what are the information are required along with the input ft, t greater than equal to t0. So ft, you have to know what is the force you have applied to the system for t greater than equal to t0, that you have to know. So that is showing by this part. So this part is nothing, that this part is involved with the input. So that information has to be known, that already we have pointed out that it is given. Now along with that, some additional information is required to know at any time t greater than t0 what is the displacement, that we have to know the initial displacement xt0, and also we have to know what is the initial velocity of the system xt0 and vt0. So along with ft, we have to know the initial velocity as well as the initial displacement of the system, then only we can describe the displacement of the system at any time t greater than t0. So let us summarize this, that what the observation we made. Now displacement xt, which is our output variable of the system or of the mechanical system at any time t greater than t0, can be computed if we know the applied force ft, that is the input variable, from t equal to t0 onwards, provided vt0 the initial velocity and xt0 the displacement are known. So these two things are very important to understand at this point, that these two additional things are required along with the applied force ft to completely describe the system output. So as a conclusion, we can say that these two variables, that is displacement xt and the velocity vt, can qualify as a state variables of the systems, because their initial conditions are required to be known to describe the dynamics of the system. And to observe once again, if you if you conclude that xt and vt are the displacement and velocity are the state variables of the system, then if you go back that how we have written the dynamics of the system, you will find that these two are the state variables of the system, and exactly the first derivative of that two variables we have expressed as as the dynamics of the mechanical system. Okay, so they are interrelated. So most of the time you will, or all the time you will find that the system dynamics are described as a first derivative of the state variables identified of a given dynamical systems. So this is a very important conclusion what we have observed from this example. Now we will move to an electrical system or electrical network to understand again, to verify or to make the clear how you will define the state variable or state variable of a dynamical system. To do that one, we have taken a RLC circuit. Many times you have encountered this system in control system 1 to find out the transfer function of the system. Okay, so the same system we have taken to analyze it to understand that what could be the state variables of this given RLC network. So suppose R is the resistor, L is the inductor, and C is the capacitor, and the input voltage. So this VI is representing the input voltage to the system, and V0, which is the voltage across the capacitor, which is output of the system. So it is also a seesaw system, and we are assuming that the current IT is flowing through the network. Okay, so now after knowing this, we can apply the fundamental laws, that is KVL, to write the integral differential equation. What is that? Now VIT, which is the input of our system, UT is equal to RIT plus LDI didt plus 1 by c integration it dt. Here intentionally I have not given any limit, because we will definitely, this thing we will discuss what could be the limit for this integration. Okay, and VT0 V0t, which is the output across the capacitor, can be written, which is indicated by YT is equal to 1 by C integration IT dt. Okay, and if we want to find out the transfer function for this system, then simply we will take the Laplace transform of equation 18, assuming all initial conditions are 0, and also we will take the Laplace transform of equation 19, assuming all initial conditions are 0, and we will find that 20a and 20b will be the Laplace transform of the equation 18 and 19. Now from there we can find out the transfer function G is equal to Ys by Us is equal to 1 by S square LC plus S into RC plus 1. So this is a second order system, and many times we have found out this transfer function in the previous course, like control system 1. Now for the simplicity, some values of these parameters are given of this network. Suppose R equal to 3, L equal to 1, and C equal to half. So here no units are mentioned, so you can assume that 3 unit, 1 unit and half unit, or also you can assume 3 ohm, 1 Henry and half farad. There is no problem. So now if we will substitute all the parametric values R, L and C in the equation number 21, then we will get the transfer function for the system G is equal to 2 by S square plus 3S plus 2, and which can be represented after partial fraction expansion, that is 2 by S plus 1 minus of 2 by S plus 2. Okay, why we have represented like this? Because we want to compute the impulse response of the system, which by definition we know that it will be the Laplace inverse of the transfer function. So if you take the Laplace inverse of GS, you will get the impulse response of the network, that is GT equal to e to the 2 into e to the power minus t minus of e to the power minus 2t. Okay, so I hope that you have understood that how by taking the inverse of GS I got the impulse response of the system. How you got that one? So we can discuss that one from our previous course, that is we know that the GS, the transfer function GS, is equal to the ratio of Laplace transform of output Y of S and U of S is the input, assuming all initial conditions are 0. So from here we can see that the YS, we can write YS is equal to GS into U of S. Now if we want to find out the impulse response, then we know that for the impulse response, so if we want to find out the impulse response, then impulse input U of S is equal to 1. Okay, so now we are finding that Y of S is equal to GS. So now if I want to find out the impulse response of the system, then we can find that the taking inverse Laplace transform, we can write Y of t is equal to G of t, which is the impulse response of the system. So this is the impulse response of the system. So from here it is very much clear that if you take the inverse Laplace, so how you got this expression? By taking the inverse Laplace of Ys, which means that inverse Laplace of G of S. So this way we can find out the impulse response of the system. So now if we will apply an input U, that is known from t0 onwards to the network, the output is given by y of t, which is the, now you see integration limit is going to start from t0 to t, g of t minus tau u of tau d tau. If the network is relaxed at t0, what is the meaning of network is relaxed at t equal to t0? It means that we are assuming all initial conditions are 0. We are not interested to know that how the past inputs which are not known to us has affected the system, and that we are not considering while assuming if the network is relaxed at t0. And how we got this y equal to yt, the system response for any input t0 onwards by this expression? Now for that we will go back to the our previous discussion. That is, we know that just now I told that y of s, the system output, is written like g of s into u of s, that I told. Now from here you can see that if I want to find that y of t, how we can find that one? Now we are finding that that will be gt convolution of u of t. Okay, and from the definition of the convolution, you know that it will be t0 to t g of t minus tau u of tau d tau for t greater than equal to t0. Fine. So now if we want to know the output yt for t0 onwards, then only we have to know the transfer function of the system, and we have to know that what is the input t0 onwards we have applied to the system. But if the network is not relaxed at t equal to t0, then your integration limit will start from minus infinity. So then yt, that is system output, is required to be known from minus infinity to t, g of t minus tau u of tau d tau. And now this similar way, what we have done for the mechanical system, we can decompose this limit of the integration in two parts. How? Now it is minus infinity to t0 and t0 to t. So now this, we are not bothered about this part because this part is known to us. If we know the transfer function and also the input is known to us, then it is very easy to compute. But what or how we will compute, or how we want to basically know that the effect of output y t0 to infinity due to the unknown input which is applied during minus infinity to t0, means initially. So to do that one, some more computation we have to do. So let us see only the part which is associated with minus infinity to t0 g of t minus tau u of tau d tau. Okay, because we want to know that how the system output will be influenced due to unknown input which have been applied during minus infinity to t0. So now if we want to do that one, so minus infinity to t0 g of t minus tau u of d tau can be easily calculated, because we know the gt. What is gt? We have calculated GT, we have calculated what? The GT, if you see the earlier expression, if you see, that is 2 into e to the power minus, that is equation number 23, 2 into e to the power minus t minus of 2 into e to the power minus 2t. Okay, so we have substituted, or rather we have computed for the g of t minus tau, and then we are finding that the final expression will be 26, where the c1 and c2 has been defined. Now you look the equation number 25 very closely, that to know that output yt for any time t greater than t0, then we have to know what is the input have been applied for t greater than equal to t0. Along with that, we are finding that the initial condition, which is from minus infinity to t0, is depending on two factors, that is c1, another is c2. So what are these c1 and c2 are? What are these c1 and c2 are? So by the expression of c1 and c2, we cannot understand. You see, this the expression of c1 and c2 is given by minus infinity to 0 e to the power tau u tau d tau. So we cannot understand what are the physical variables the c1 and c2 are depending on. By looking the expression number 27, we cannot say that one. So to understand that one, little bit further calculation we have to do. But before that, we want to say that note that c1 and c2 are independent of t. Hence, if c1 and c2 are known, the output y of t after t greater than t0 excited by the unknown input during minus infinity to t0 is completely determinable. So the output y of t can be calculated for t greater than equal to t0 if we know the values of c1 and c2. But it is not understandable by looking the expression of c1 and c2 that how or what the physical variables of the network they are depending on. To understand that one, more further discussions are required. So now we want to calculate y of t0, the expression of y of t0. So what will be the output exactly at the t0 instant of time? So go back to the expression of y of t. So if we want to calculate y of t0, then this part is going to be vanished, because it is going to start from t0 to t. So we want to calculate y of t0, so this part will be vanished, and this part, that is the part which is depending on minus infinity to t0 g of t minus tau u of tau d tau, that we have calculated, it is 2 into e to the power minus t c1 minus of 2 into e to the power minus 2t into c2. So y of t0 will be simply 2 into e to the power minus t0 c1 minus of 2 into e to the power minus 2t 0 c2. So now that thing we have written in the next expression. So you see, we have written y of t0 is equal to 2 into e to the power minus t0 c1 minus of 2 into e to the power minus 20 c2. So now we will differentiate this output once. Okay, so to get one redundant equation such that we can solve for C1 and C2. So let us differentiate y of t once again. So if you differentiate y of t, so we will get minus 2 e to the power minus c1 and plus 4 into e to the power minus 2t c2, and if you differentiate this integral part, that is t0 to t g of t minus tau u of tau d tau, you will get the expression that is g of 0 ut plus integration t0 to t partial derivative with respect to t g of t minus tau u of tau d tau. Fine. Now again we want to calculate y dot of t0, and at that time we are assuming that z0 is equal to 0. That also is that also can be verified, the expression of gt. You see the expression of gt, if you see what is the expression of gt, so gt is equal to minus 2 e to the power minus t minus of 2 into t to the power minus 2t. So if you calculate z of 0, that is also will be equal to 0. So now if you assume that z0 is equal to 0, then y dot of t0 will be simply minus 2 e to the power minus t0 c1 plus 4 into e to the power minus 2 into t0 c2. So now this will be vanished, this part will be vanished, because you are calculating the y dot of t at t0. So this you are calculating at t equal to t0. So that's why this part is going to be vanished, and already from the calculation I have shown that z0 is equal to 0. So this part is also going to be vanished, this part is also going to be vanished, so we were living with only this part. So now you closely look the equation number that is 28, this 28 and equation number 30. So we got the two equation, and from here we can calculate what is C1 and C2 in terms of y of t0 and y dot of t0, and that exactly we have done in the next slide. Here you see we have computed C1 and C2 using 28 and 30. Now you can, by observing the expression of this is an alternative expression of C1 and C2. You see previously we have got the expression of C1 and C2 earlier. Let us see the equation number 27. But from here it is not understandable that on the physical variables of the network how the C1 and C2 are depending on. But now the expression what we have determined, it is easy to know that how the C1 and C2 can be calculated. Now you see the C1 and C2 are depending on y of t0 and y dot of t0. Both the C1 and C2 are depending on y of t0 and y dot of t0. So let us see what is y of t0 and y dot of t0 is. So now can you remember that y of t, we have defined the system output, that is the voltage across the capacitor. So it is 1 by c integration it dt. So now it dt. Now if I will ask that what is y of t0, so that is basically the voltage across the capacitor. And what will be the y dot of t0? So that is actually the current which is flowing through the inductor. Fine. So now with the expression of C1 and C2, again we have written the expression of output yt. And now it is very much clear that to determine the output y of t for t greater than equal to t0, we have to rely on the quantities like, or the variables like input variables. We have to know the input variables. So this part is showing that we have to know u of t for t greater than t0. Along with that, we have to know that what is y of t0 and what is y dot of t0. Means we have to know what is the initial voltage across the capacitor and what is the initial current through the inductor. So we can see that if y of t0 and y dot of t0 are known, the output after t greater than equal to t0 can be uniquely determined even the network is not relaxed at t0. Hence the numbers y of t0 and y dot of t0 qualifies as the state of the network at t0, means state variables of the network. Clearly the set C1 and C2 also qualifies at the state of the network, means not only y of t0 and y dot of t0, C1 and C2 can also qualify as a state variables of the network. Means here another thing we want to point out, that for a network or for any dynamical systems, the choice of state variables are not unique, means multiple set of choice of state variables may exist in a dynamical system, but that thing we will discuss subsequently, not now. But one thing it has been clear from this analysis is that to know the system output completely for t greater than equal to t0, we observe that for this dynamical system like electrical network, the voltage and current in the networks are required to be known, and they will qualify as a state variable of the network. So that's why initial current through the inductor and initial voltage across the capacitor, for any driving voltage the behavior of the network can be determined uniquely if we know these two quantities. So what are the state variables for this example? The inductor current and the capacitor voltage, means simply Vt, means the voltage, capacitor voltage we have indicated by Vt, and current, inductor current, we have indicated by It. So these two variables in the network can play as a state variables or the internal variables of the dynamical system. Okay, so now formally we will define the state, because with these two examples it has been clear that to whom we will qualify as a state variables of a dynamical system. The state of a dynamical system is the minimum amount of information at t0 that, together with the knowledge of the input u t0 onwards, determines uniquely the behavior of the system for all t greater than equal to t0. Okay, and examples are, what are the examples of state variables? The or state, that is displacement xt and velocity vt of the cart are the state variables. The voltage across the capacitor vt and the current through the inductor it are qualify as a state variable. So now as we have claimed that these two examples what we have taken, they are the second order. So the minimum number of state variables we have identified two. So we can generalize it. If we have a nth order differential equation, then there exist at least n number of state variables. So now how to represent or how to represent this n number of state variables in a compact form? Then we have to take the help of the vector notation. So that's why now we are going to define the state vector. So once we have identified n number of state variables of a given system, then the n number of state variables can be the n components of a state vector, that is xt. The nth order system have n number of state variables. The n state variables can be considered as an n component of the state vector xt, described in n dimensional vector space or the state space. At this point maybe the vector space is not clear to you, but in the due course I am going to take one or two lectures about the vector space. Then it will be also clear why it is called state space, why it is called space. That also it will be clear later on. Now you see how mathematically we will write. Now xt is the state vector whose dimension is n cross 1. So xt is the vector which having n number of component x1t, x2t, xnt. That's why its dimension is n cross 1, and all these are real, and that's why the symbol we will write xt belongs to R of n. It means that in the vector space of nth order, they are the vector space of all real numbers, and we will take the x1t, x2t, xnt from the vector space, and we will construct the state vector in this way. So this is the meaning of this, the representation xt, which is represented in equation number 33. And what are the example? In case of mechanical system, we have identified that xt, the displacement, and the velocity are the state variable. So we can say that the xt, so this xt, you should not okay, to clear your doubt, what we can do, we can write this one as x bar of t. Okay, so now suppose x bar of t is equal to xtvt. It means that we have taken a state vector x bar of t, which having dimension of 2 cross 1, and it having two components, that is the xt and vt. Similarly, the electrical network, we know that we have identified the capacitor voltage vt and the current through the inductor it are the state variable. So the state vector xt having two component it and vt, and its also dimension is 2 cross 1. So if it is a second order system, then at least we can have two state variables. So that's why we have represented by choosing the state variables for the system, and using vector, and we are representing it in a vector matrix notation. Okay, so now we will move further, that is to define the state space. So this state space definition we are giving, but definitely when I will discuss the vector space, then I will correlate why it is called state space. The definition of the state space, what is the definition? The n-dimensional space whose coordinate axis consists of x1 axis, x2 axis, xn axis, where the x1, x2, xn are the state variable, is called the state space. Means you can imagine that when we have the two state variables, that is the voltage and current, and they can be represented the two axes in a space, that is suppose x1 axis is the voltage and x2 axis, that is the current, and now these two coordinates are the coordinates of the state space, and the state of the system called the can be represented by a point in the state space. If the state x, one example has been given, if the state x is considered as an element of an n-dimensional vector space, then this vector space is also called a state space. The state of a system for time t can then be represented as a point in the n-dimensional state space. The curve of all these points in the state space for variable time t in a time interval is also known as trajectory. So now we will consider a figure to understand the system trajectory and the state space, which is three-dimensional. So here you see for a state vector, suppose we have taken a state vector xt which having three component, that is x1t, x2t, and another component we have, that is x3t. So now we have the three component, and the three components are the three axes of state space, that is x1, x2, and x3 at any point. So now from any initial conditions, the state trajectories are evolving with respect to time. Now at any point on the trajectory is representing the state at any time t, and that is x1t, x2t, and x3t. So this is the concept of state space. So now I will end here summarizing that what we have discussed, that you see we have started with to identify that if we will assume for a dynamical system initial conditions are 0, then what wrong can happen. From there we have tried to understand that what are the state variables could be for a dynamical system. Then we have taken the example of mechanical system, and then we have understood that any time if we want to know the displacement t greater than equal to t0, then we have to know the input, that is the force t greater than equal to t0. Along with that, we have to know the initial velocity and the initial displacement. So these two quantities can be qualifying can be qualified as a state variable. Similarly, for the electrical network, we have observed that anytime the output, that is the voltage across the capacitor, if we want to determine, then not only we have to know what is the input voltage we have applied, along with that we have to know that what is the current through the inductor and what is the initial voltage in the capacitor. So these two variables, that is IT and VT, will qualify as a state variable of the network. So then we have given the formal definition of the state, then state variable, state vector, and state space. And next class I'm going to discuss that one claim we made in this lecture, that nth order differential equation can be represented in number of first order equation with the help of state variables, that we are going to discuss in the next class. And then also it will be clear that that from the definition of the state variables, that in a nth order differential equation, to whom we will call the state variables. So I will stop here. We will meet in the next class.